Welcome everybody to this presentation. I am Paola Mazzanti and I'm a wood technologist from the University of Florence. And let's say for the last 20 years I dedicated myself to the scientific conservation of panel paintings. And this is the focus of my presentation, which is about the experimental tests for mechanical properties of wooden buttons used for attaching auxiliary supports behind panel paintings. But before focusing on the specific topic of this presentation, I'd make a brief excursion on what panel paintings are. I'm sure everybody knows that the most famous artists from Renaissance period painted on wood. And here in this slide you can appreciate three examples of panel paintings. Three that I choose among many others, of course, just to show you the variety and their complexity. For example, here you see the Medusa shield by Caravaggio, which is peculiar for its shape, or here a large crucifix by Giotto, which is 6 meters by 4, or again here you have a polyptych, which is a complex artwork with all these cusps, for example. And when we can observe the back of all these artworks, that is what we see. We see wooden boards glued together. Of course, we can't see absolutely the back of the Caravaggio shield here because it's painted back and front. However, this drawing is a 3D reconstruction based on a reality scan. So this is exactly what it is, and as you can see, it is made again by thin wooden board, in this case, glued together. However, when we focus on the crucifix or the polyptych, we can also appreciate the restraining system with which they are equipped, and it is made of cross beams or sometimes frame. The restraining system is part of a panel painting, of course, and was originally designed with a double function. First, it contains the hygroscopic deformation the panel painting undergoes every time the climatic condition varies. And also it provides, of course, a certain structural unity for handling and movimentation. For this slide I've prepared three simplified drawings to show you a few examples of original crossbeams. Here you see, let's say that until the early 15th century, the first crossbeam system that was planned was the nailed one, here, this one. The connection is between the crossbeam and between here the crossbeam and the wooden panel is granted by nails here and here that were typically inserted from the back here and were clinched back on a U shape into the wood from the front, so this way. However, these nail connections produced punctual forces on the wooden panel, which was prevented from forming both in plane and out of the plane. And such problems were fully understood by both artists and artisans of that time. And thus they changed the connection system to one characterized by a distribution of forces on the wooden panel, like the two examples you have here. This is the wooden rigid crossbeams, where a crossbeam is mounted among these small pieces of wood. And this is the dovetail crossbeam, is here, which is directly inserted in the wooden support in this way. Maybe with this, maybe this development was due to the idea that these two systems allow a certain freedom for the in-plane deformation. However, when the crossbeams were not well designed, we have important consequences on the panel paintings, as the one you see in this slide. For example, if the crossbeams are too stiff and wooden support, the wooden panel cannot deform when it's subjected to climatic condition variations, both the paint layers and the wooden panel show a general condition of suffering, and these two images confirms that. For example, here you see buckling, or here cleavage, also lifting of the painted layers, which are caused by compression when the wooden panel cannot swell. And on the contrary, when the wooden panel is prevented from shrinking, cracks can occur on the wooden panel, and as you can see here, they are sometimes visible on the paint layers too on the front. So if the original crossbeams were lost, for example, or as I said before, were not adequate to guarantee an optimal conservation of the panel painting, the restorers have, of course, to modify them for its good conservation. And I can say that in the 80s of the last century, the restorers from the Opificio delle Pietre Dure, with whom we have strictly cooperation, proposed a new method, which is today well known as the elastic auxiliary support. Here you have a photo of a mock-up panel made for educational uses only, which is equipped with two elastic crossbeam, one here and one here. This other photo shows you a section cut here of the elastic crossbeam, and you see again the wooden support, the wooden crossbeam, and the connection here. And these exploded drawings show all the components of the elastic support system. You have once again the wooden support here and the wooden crossbeam with the wooden button here, which is the component glued on the wooden support, which guarantee the connection between the crossbeam and the wooden support. In the button, a screw was strapped in, and this screw is free to rotate, which guarantee a certain freedom for the in-plane deformation. Moreover, spring here is connected, is mounted on the screw, and the spring cooperates with the crossbeam, of course, to the elasticity of this system. And finally, retaining nut here to close the connection. And in this slide you have an example of how the elastic crossbeam works. Here you see a cross-section of a panel painting and elastic crossbeam here. And let's say that this panel painting undergoes a decrease of relative humidity, and you see that a larger quantity of moisture here is lost from the back than from the front here, where you have the paint layers which are less permeable than the back. So in this situation, the painting panel deforms with a convexity on the back. and the cross beam here reacts to this deformation, and the connection here on the center, like this one, show a large gap, of course, between the cross beam and this wooden support, and a spring which is compressed. On the other hand, when you are on the periphery here of the panel, you could have this situation where the wooden support and the cross beam are in contact, and this spring, which is mounted, of course, always preloaded, is not compressed further. I show you this slide again just because I want you to focus on the button, this element, which is a wooden component that is the focus of this presentation, and here you have two other drawings of the same element. So now the aims of this researchers on this presentation are the study of the mechanical behavior of the buttons, to give information to restorers for a proper design, and also to analyze the influence of the geometry and wood density on the mechanical properties of the buttons. That is why we tested more than 300 buttons and subjected to pull-out mechanical test. We tested 4 wood species, oak, lime, beech and walnut, and also the MDF panel. We also chose 3 different geometry. Here you have geometry A and B with a counter bore hole for the head of the screw and a steel washer inserted for distribution of the load. You have this geometry named C with a countersunk hole and no washer, and you have again this geometry named TC for truncated cone with a countersunk hole here for the head of the screw and a truncated cone for the external shape. We tested 3 different diameters, 20, 25 and 30 millimeters, and 4 aids, 3, 4, 5 and 6 millimeters, with different residual thickness. That is the dimension which changes, and I'll point out now what the residual thickness is, named H1 in the drawing, and is exactly the thickness of wood above the head of the screws, so this one, which is above the head of the screw. The buttons were glued on a beech board with epoxy resin, and the screw trapped in the button here, which is free to rotate of course, was connected to our university testing machine to perform the pull-out test, of course, and both force and deformation were measured. The data were organized in force deformation graphs, like this one you have here on the left. And specifically, this graph shows how the different geometries behave for this test. We see that the geometry A and B, that is the counterbore hole and a washer inserted inside, show a similar behavior. You have this and this. The difference here in the ultimate load value is due to only to the different residual thickness. On the contrary, you have here geometry C with a countersunk hole, shows a very different behavior, mechanical behavior, with larger deformation and higher ultimate load. Here on the right, you have another two graphs showing you that the two geometries here we tested, the cylindrical one and the truncated one, does not affect, show no difference in the mechanical properties here. These other tests you see here are about some preliminary tests we made on a few buttons only, and to see the influence of the density of wood, and see that if we compare the same geometry, for example geometry C here, so countersunk hole, you see that the oak and the beech have higher value, ultimate value, than, for example, lime here, and of course some MDF here. These other graphs show the influence of the diameter on the left and the residual thickness on the right, on the mechanical properties, of course, of the buttons, but for only the oak buttons with a countersunk geometry. I have to highlight that because of a non-homogeneous distribution of the specimens throughout the density, we thought necessary to divide both ultimate load and stiffness values by density. So we have the specific ultimate load here and here, and the specific stiffness here and here. These tests show that the diameter, you can see here, have no influence. The variation of the diameter have no influence both on the ultimate load, specific ultimate load, and specific stiffness. However, we have influence of the residual thickness that here increases on the specific ultimate load. Here you have a graph, it's quite clear. But again, we have no influence, neither of the residual thickness on this specific stiffness. This last graph shows the failure types we identified on the buttons with a qualitative observation, and we grouped all these buttons in two main groups. One on the left with the thinner buttons, which failed simply because the head of the screw breaks through the wood, and here you have a photo, but this is not can be considered as a real failure, and you see here in yellow. On the right, here we have the thicker specimen, thicker buttons, which underwent, on the contrary, underwent a real failure because we observed a clear detachment of wood, which was as a rectangular piece here in orange, and here, or a whole ring here that is in blue, here, this and this other. With this slide, I would propose an hypothesis on the causes of failure of countersunk buttons only, even if such hypothesis is based only on the qualitative observations. Let's say that we observe that the initial part of load deformation curve is mainly affected by embedding of the head screw in the wood, and this causes damages of the buttons, of course, and It also could explain why we observed no influence of the dimensions on the mechanical properties. Afterwards, when the load increases, the thinner buttons quickly fail for breakup through, while the thicker one bear higher load values before failing, because a combination of other mechanisms is clearly involved and probably is concentrated. This mechanism are concentrated on the wood around the screw head. The cleavage is certainly involved, together with probably the tension perpendicular to grain when a whole ring detaches from the button, to which we should add the rolling shear when a rectangular piece of wood detaches. So to conclude, all the mechanical phenomena which cause the failure are localized around the head of the screw. Thus, the diameter does not influence the ultimate load. The residual thickness is the only variable which influences the ultimate load, and nor the diameter of the button, neither their residual thickness have any influence on stiffness, and depends only on the embedding of the screw head into the wood. Also, the observed failure mechanism is different for thinner and thicker buttons, as just explained. Since the former failure is the result of the breaking of the screw through the thickness of the button, and the latter is mainly caused by cleavage together with rolling shear and tension perpendicular to the grain. Moreover, no influence of the external shape has been observed, while the density of wood influences the ultimate load. So thank you very much for your attention. That is me finally, and I also had my email address in case you have any questions or doubts to share. Thank you very much.